Okay, good morning to everybody. Today we are going to finish the lecture number 5, the second part, and the topics of this lecture 5 is interaction between the electromagnetic energy and the surfaces. In the first part of the lecture, we introduce all the topics related to the geometrical aspect of the reflection coming from the surface. While in the second part, we are introducing the topics related to the spectral characteristics of this kind of reflection. So we will start with this part. So, in order to approach the spectral characteristics of the reflection phenomena, we need to introduce the concept of spectral signatures. Spectral signatures that are of fundamental importance for remote sensing, and trust me, they are very, very important. They are the representation of the reflectivity variation as a function of the wavelength of the reflected electromagnetic energy for homogeneous surfaces. So, just an example is given in this diagram. So, in this diagram, as usual, on the x-axis we have the variation of the wavelengths. In this case, you see, we are starting from 0.4, look at the mouse here, from 0.4, that is the blue, till 2.5 microns, that is the mid-infrared, and here, up on the x-axis, you see we have the spectral bands, so blue, green, and red of the visible, near-infrared and middle-infrared, and we are referring only to all the spectral bands where reflectivity is involved. So you see that in this diagram there's no any thermal infrared reference, because we mentioned the facts that in the thermal infrared sensor generally are registering emission coming from the ground, while here we are only considering reflection. And in the y-axis we have the reflectance in percentage here, you see from 0 till to 60%, but of course we all know that instead of reflectance we can mention on the x-axis the variation of the reflectance coefficient, that is the rho, so ranging from 0 to 1, and we have something that is very similar. So you see the concept of spectral signature, starting from the name of these topics, means that it is something that is related to spectral, so to the function of wavelengths, in which wavelength, of course, it's a function because they are ranging in the different wavelengths, and signatures because like our signatures, all the reflectance, the variation of the reflectance for every single homogeneous surface on the ground, on the Earth's surface, is like our signatures. So that means that are really different from each other. And if you have some reference to this particular spectral signature, that is an unknown signature, you can understand from how this signature is ranging in the different wavelengths to understand broadly what kind of surfaces you are facing. And so you see we have different here spectral signature. For example, here we have turbid river water or clear lake water, and you see that in this case these spectral signatures are very low. That means that are very has a very low reflectance value. That means that being all these surfaces as acquired from satellite opaque, that means that they have a transmission coefficient equal to 0. If they are not reflecting, of course they are absorbing. So you see that water in general is a very good absorber of energy. And you see that starting from the near infrared, water, both turbid or clear, is a very good absorber in the infrared. That means that it's very similar, as we mentioned several times, to a black body for the near and middle infrared. Then here you have, for example, with this maroon and orange spectral signature, apart from the fact that you see the dry soil with the 5% of water content and the wet soil, that means the same soil with the 20% of water, you see that they have a very different curve, especially in the infrared. And you see that, when there are much water, as in this case, you see being the water a very good absorber, the same soil with the larger quantity of water is reflecting less energy. And you see that the shape of the curves are very similar to each other. But the second one is represented by the fact that wet, and so water content, is absorbing energy. While here, in green, you have this particular spectral signature that you see is the signature of a generic vegetation, where you have, for example, in the green band of the visible, a relative peak of reflection, then you have an absorption peak here in the red band, and then a very high peak that is 3 or 4 times more than in the green, in the near infrared. And you see then in the in the middle infrared, the vegetation is going to reflect less energy than in the near infrared. So these are examples, and of course there's nothing more to say from the theoretical point of view on spectral signature, because these are behavior from the reflectance point of view. That is the characteristics of the physical, chemical characteristics of the different surfaces that we have on the ground. So it's not there's really nothing more to say concerning the general behavior, but we have more to say if we are interested in checking which are the classical spectral signature for particular materials or surfaces. So, for example, now we can start to check more in depth spectral signature, in particular spectral signature, as you can read here, of water, snow, and ice. Because among the most recognizable environmental categories in remote sensing, water and its solid states play a special role. So, all this part here is related to spectral signature and characteristics of the water and the solid state of the water, that is snow and ice, and in particular also the snow in its different metamorphism. That means how, for example, snow is accumulated on a surface could be easily understood, taking into account the different spectral signature. This on the basis of their specific behavior, of the water and the solid states of water itself, in the different part of the electromagnetic spectra, generally contrasts with the other element of the landscape. Because, as you already saw during the labs, the water, as the vegetation, has a very different spectral signature in comparison with other surfaces that we have on the Earth surface. So, when observed in small quantities, pure water is a substantially colorless element, which justifies its very low reflectivity and high visible transmissivity. In the observation of a water body, it is necessary to consider that the different contributions that make up the outgoing radiance. So, when we are recording the radiance coming from the water, especially when the water is reflecting energy for passive sensor coming from the sun, from our external source of energy, we need to consider that the water is reflecting energy from different layers of the water itself. In fact, the irradiance coming from the sun together with the diffuse one due to the irradiance coming from the sky, for example, during a very clear for a very clear sky, we have, of course, the Rayleigh scattering or the selective scattering. So we have also a reflection that is coming from the sky itself in the impact of a water surface. So these two kind of irradiance coming from the sun and coming from the sky, for example, by means of scattering, selective or non-selective, when they are impacting on a water surface, breaks down according to different interaction mechanisms. A scheme of such interaction is represented in the following figure. So, when we are omitting the dependence on the angle of illumination and observation, so we are not taking into account the surface that is reflecting energy and the surface, the area of the detector that is collecting energy. The radiance L, of course, that is function of lambda, observed by and acquired by an instrument that detects a surface of water, is composed of four main components that are defined in this equation. So you see the total amount of radiance that is coming from the water is the sum of the radiance that is coming from the atmosphere. You see here that is the energy that is scattered by the atmosphere, that is not going to strike the water surface but is going directly to the sensor without any interaction with the water. Then we have the sum of the radiance that is coming from the surface of the water, you see here. Then the radiance that is coming from the water, the L water, that you see is something that is in the middle of the water, especially if we have a very thin layer of water, and then the radiance that could come from the seabed, so from the depth of the water, when the water is in contact with a solid state. So, I mean, when we are registering and when we are recording these quantities, we need to take into consideration these three components that are in Italian actually in this figure, that are aria, that means that is air, water, aqua, and fondo, this is the seabed. So I mean, the energy is passing through the three medium, and with this three medium has different interaction. For example, with air, of course, we have the interaction, classical interaction with the atmosphere, then the interaction with the water, that is what we are actually need, and then the interaction with the seabed, that is the classical interaction with surfaces. All right, so the fraction of energy, the L, ATM, that is coming from the atmosphere, and of course its function that is depending on the wavelengths here, is the fraction of radiance that cannot reach the water body and is reflected by the atmosphere interposed between the sensor and the water surface. In this case, in the case of large distances, as can be from an airplane or satellite, this quantity can be much greater than that of interest L water, as shown in the following figure. So I mean, usually this quantity, especially for the visible bands, where you remember talking about scattering, that is a reflection in all the direction due to the aerosol or the particles that are suspended in the air, the quantity of energy could be much more, the quantity of energy that is reflected could be much more of the quantity of water, of energy that is reflected by the water. And so that could be a problem if we are interested in characterizing the sea surface. Then the energy that is coming from the surface is the fraction of radiance reflected by the water surface, and which cannot penetrate the water body. it is therefore the component most closely linked to the light diffused by the sky. So what is coming from the surface of the water, for example, do you remember the images of the northwestern Italy we analyzed in the first labs? I mean, you see that in the visible, that water is very bluish. So that means that, what we are getting from the sensors is this fraction of radiance. So the fraction of radiance that is coming from the surface, and in this case, this fraction of radiance is something that is related to the reflection of the color of the sky over the water surface. So you see that in real cases, this L SIR, that is what is coming from the surface, is very important. Then the L water, that is again function of wavelength, is the fraction of reflected radiance that penetrated the water body without being able to reach the bottom. This is the component of greatest interest in the study of water because it is directly linked to the first thickness of the water column and to the processes of absorption and diffusion of irradiance in the volume of water. So this is very strange. The L water and the L seabed that we will see later on is something that is quite strange for us because I mentioned several times that when we are involved in the acquisition of radiance coming from the Earth's surfaces and when we are acquiring this radiance from detectors that are mounted on board a sensor of satellite, from that kind of distances, several hundreds of kilometers, all the surfaces on the ground we mentioned that are opaque. So that means that the transmission coefficient is equal to 0. And this is a very good thing for us because when we are analyzing images, if we are facing bright cells of the image, that means that these surfaces are reflecting energy. When we are facing dark part of the images, that means that is prevailing the absorption coefficient. So these surfaces are not reflecting energy. So it's very simple to understand which is the behavior of the surfaces. But it is simple only because we are taking into consideration only two coefficients. And of course, if one is close to 1, the second will be close to 0 and vice versa. While if we have three different coefficients, so if we are adding the tau, the transmission coefficient, it's not so simple to understand what is happening on the surface. This is the case, for the water, especially when we have a very thin layers of water, that means a few tens of centimeters, not more, because otherwise the surfaces are opaque. When we have very thin layers of water, we can get a radiance that, as is stated here, is coming from the inner layer of the water. So and this is very important because we can understand the turbidity of water, for example. And again, if we are considering the last component, the L seabed, of course, again, function of lambda, this quantity is the fraction of radiance that has managed to penetrate the water body, reaches its bottom, and re-emerges. Its contribution depends on the transmissivity coefficient of the water and its thickness, of course. And of course, the transmissivity coefficient, the tau coefficient, of course, should not be 0, is more than 0, of course. And the thickness of the water is very thin. A few centimeters. Otherwise, again, the water is an opaque body. All right, in any case, the components of the previous equation, different from the L water, the most important information needed, turn out to be a disturbance and undesired. The most arduous task of aquatic remote sensing lies precisely in isolating the radiance of interest from this component. So if you are interested in how the water is reflecting energy, of course you need, you see, to extract what is coming from what we call the L water. And so we need to, that is actually in this diagram here, the curve that is in bold, that is thicker, what is called here L arc, that is the L water. So I mean, you see, we need to try to isolate, of course, the L ATM, so the radiance that is coming from scattering of the atmosphere, but you will see that this component could be easily isolated by the radiance that is coming from the sensor, while it will be more difficult to try to isolate these two components. So the radiance that is coming from the inner of the water and the radiance that is coming only from the surface of the water. And this is, you see, is something that is related in this diagram only for the visible part of the of the electromagnetic spectrum. All right. The portion of energy reflected by the water, when it's pure, can reach a maximum of 3% of the incident radial flux, and is confined mostly to the bands of blue-green light, from where a continuous decreasing is observed going towards the lengths of longer waves, until completely absorbed already from the near infrared. So when you see, for example, the previous figure, so you have we have to mention here in bold that there's only a very small fraction of energy that is reflected by the water, because you see, it's in all the bands is a very good absorber of energy, and the reflection of this water, the small amount, is only in the very short wavelengths of the visible. So mainly in the blue-green part of the visible spectrum, while starting from the red part, and especially in the infrared, the water, as we have seen, is a very good absorber of energy. So the color of the water, therefore, is not an intrinsic property. Of course, it's not the water that appears is blue, but depends almost exclusively on the influence of the surrounding environment, such as the color of the sky, of that of the seabed, if we have very thin layers of water, and the results of the diffusion caused by the presence of compounds such as phytoplankton, for example, suspended sediment, the organic component of other surfaces. So I mean, the color of the water, of course, is not an intrinsic properties of a surface, but of course no surfaces have an intrinsic property related to colors, but it's only the way the colors that is appearing, the way in which these surfaces are reflecting energy. So I mean, the water is not blue, of course, the water of the sea, because it's blue when the sky is very clear, appears to be grayish when the sky is very cloudy, and of course appear to be black when during the night, because of course it's not reflecting nothing that is coming from the sky, because the sky in that situation is actually dark. All right. Concerning the solid state of the water, that is snow and ice represent the solid state of water, and their high reflectivity value is one of the most important features in Earth observation. So you know that, for example, the water is representing most part of the Earth surface, both in the liquid state, that is the main I'm sorry, is the main surface that we have on the Earth's surface, but also snow is very represented, especially in the very high and very low latitude, considering, for example, the pole. And so it's very important for the Earth observation. The snowpack is made up of a series of superimposed layers of snow, snowfall or wind deposits, for example, that have different physical and mechanical characteristics depending on their state of metamorphism. In this case, in the case of dry snow, for example, snow with a temperature that is less than 0 degrees in Celsius, the evolutionary processes of the snowpack can lead to the rounding of the faceting of the crystals. So, we have this classical fractal shape of the crystal. When you have different layers of snow, of the snowpack, that can cause, due to the mechanical forces, the rounding on this faceting of the crystals. And so when, on the other hand, due to heating, the snowpack increases the snow temperature up to 0 degrees Celsius, the function processes that take place led to the formation of wet crystals. And these crystals, in the different shapes that can assume, can have different mechanisms when reflecting energy. And the shape of these crystals and the condition in which the different layers of snow on the snowpack are formed is something that is related to the metamorphism of the snow, so how it's changing during time. The optical properties of the snow cover in the visible and near infrared depend on some specific factors of the composition and structure of the snow and its metamorphism phase. Amongst these, what is really affecting the reflection of the snowpack is the size of some crystals, the thickness of the mantle, the density, the presence of impurities, and the content, of course, of water. The reflectance of the fresh snow is very high in the visible and in the near infrared, and decreases strongly in the medium infrared, giving rise to a well-distinguishable absorption structures at wavelength greater than 1 micron, and in correspondence with the water absorption bands in 1.4, 1.9, and 2.6 microns. And you can see here in these figures. So you see, these are very different metamorphisms of the snow. You see here up we have fresh snow that you see. Again, on the x-axis we have wavelengths, and on the y-axis we have reflectance here. So we have the rho coefficient ranging from 0 to 1. You see that fresh snow is a very high reflectors of energy. Of course, we are in the visible, for example, for us the snow is whitish, so that means that is reflecting the same quantity of energy in all the subbands of the visible in a very high quantity, so it's very close to 1. So this is the fresh snow that you see here in the near infrared. In the mid infrared there are absorption peaks, where when we have different metamorphisms of the snow, firm, glacier ice, or dirty glacier ice. That is, dirty means that we have impurities, for example, coming from vegetation or from particles of the atmosphere. You see that in this case the reflection is changing a lot. For example, you can, of course, if we have images in these different wave in these different spectral bands acquired by satellites, of course you can understand that it will be possible to distinguish between fresh snow and, for example, dirty glacier ice. All right, so changing the topics, I'm sorry, and going to a spectral signature, but for other things, we can introduce the concept of what is is happening for soils and rocks. But wait a moment, I just need to check if everything is going on okay with the registration, with the recording. Okay, we are half an hour. Okay, concerning soils and rocks, what is happening with soils and rocks? Soil, especially in the higher horizons, can be seen as the residual product of the transformation of the underlying mother rock. In favorable exposure conditions, for example with no or very small vegetation cover, and in technical terms, when we are referring to remote sensing techniques, these conditions, so with that are soils or rocks with a very small vegetation cover, we talk about bare soil. So that means that, we are not characterizing really the soil, but we are characterizing a surface that is not covered by vegetation or water, for example. So it's a very bare soil without any vegetation. In this case, the reflectivity curves of the different soil types offer important information on their characteristics, and such as the concentration in iron oxides, the moisture content, which is linked to the granulometry and therefore the porosity of the medium of the soil itself, the presence of organic elements, and these are the three main characteristics we can extract from data acquired from satellites. In the first case, that is the concentration of iron oxides, with the increase of the concentration of oxides, there is a chromatic shift towards red-orange due to the absorption of blue and green radiation by the granules and spheres of which an oxidized soil is composed. This is the case of lateritic soils present in the tropical bands and in a hot, humid climate. So, when you are observing, for example, soils, especially in the visible, that have these orange-reddish colors, so that means that, of course, it's reflecting more in these subspectral bands of the visible, while in the blue and green, as is mentioned here, the radiation that is coming from the sun is absorbed by these granules and spheres of which an oxidized soil is composed. And the color of the soils can give you some very important information concerning the concentration of iron oxides. While the presence of other two components, for example the moisture content and the organic matter, in most cases lowers the value of the spectral reflectance, which in the visible corresponds to a tendency towards dark tones. For example, you see, and we all know that the water content, the moisture content, having water, much is the water in the soils, much be the absorption that is due to the water itself. And so, for example, you see here, when we are checking the reflectance, the spectral signature, and here we have ranging the reflectance, the percentage of reflectance, ranging from the blue band to the mid-infrared band, and you see we have different soils. You see that, for example, if we are taking into consideration the curve B, that is fresh soil, and for example the curve A that is organic dominated, or the curve C that is iron altered or organic affected, and D and E the iron rich, you see here they are lowering generally the presence of other substances and water especially. They are lowering the reflectance. You see, I'm sorry, the curves have all the same shapes, but you see, so it's a sort of set of parametric curves, but the contents of organic matter, of iron dioxide and of water is lowering the reflectance coming from the same surface. Furthermore, there is a sudden bending of the reflectivity curve in correspondence of three water absorption bands, again, that are centered in 1.4, 1.9, and 2.6 microns of wavelengths. So, these absorption peaks of the water are very important for most part of the surfaces that are present over the Earth's surface. This bending, which is actually naturally proportional to the moisture content of the soil, Therefore, a multispectral analysis in these bands, compared to the contiguous one, is an excellent tool for investigating the subject. In fact, the soils, being the results of the transformation processes of the underlying mother rock due to the combined effects of atmospheric agents and biosphere activities, can show very specific spectral responses as a result of the combination of a certain number of elements that compose them. So, for example, minerals, matrix, iron dioxide, organic material, and water. Although the reflectivity of soils can range in a fairly wide range, a series of measurements made on more than 200 types of soils has shown how their general shape is maintained. So this is related, of course, to the presence of other minerals or other particles of water in the soils. But here it's very important to mention the fact that after many measurements of different horizons and of different soils, I mean the general shape of the spectral signature is maintained, and as mentioned before for the previous figures, if you have, for example, an higher moisture content of the water, the shape will remain the same, but I mean just shift towards lower reflectivity coefficients. Compared to those of soils, the spectral reflectivity curves of the rocks, being composed of different minerals and with very variable structures, are less generalized and consequently of more difficult interpretation. So I mean, for the soils, you see, we can convey to a uniform spectral signature, of course. As you can understand, the rocks are a very difficult generalization. I'm sorry. In fact, there are multiple combinations of curves depending on the various parameters and aspects that can be considered, from the color to the type of rocks, from the structure to the mineral content, etc., etc., etc. For example, two families of granites can be distinguished spectrally based on their different structure rather than on their different colors. To which the silica content is bound, and for this same parameter, not in all wavelengths. On other remotely detectable physical quantities can be discriminating, such as the thermal inertia, for example, or thermal constraints, according to which a rock cools and therefore also typically heats up. So you see here, for example, you have different kind of rocks, and of course, again, on the x-axis the wavelengths, on the y-axis the absolute reflectivity in this case. And you see that if we have quartz, diabase, sandstone, quartz, another kind of quartz, basalt, granite, and limestone, you see that the spectral signature are very different. So I mean, they have actually a similar trend because they are increasing the reflectivity with longer wavelengths, but you see that I mean, in the middle is happening something very different. So I mean, you see, this is not really a diagram that is representing a parametric variation, changing of the same curves, but there are very different curves. So I mean, this is due especially for what we mentioned before, so that for rocks, it's very difficult to generalize a single spectral signature. We mentioned the fact that the thermal capacity and thermal inertia are among the distinctive features often used for the realization of classifier in remote sensing. for the distinction of soils and rocky lithotypes. In the first case, or thermal capacity, the granulometry and their matrix clearly regulate the emissivity epsilon, highlighting in the medium infrared band of ranging between 3 and 5 microns a clear distinction between sandy and silty soils, where in the rest of the thermal infrared range the soil silty shows the same trends as the sandy one. The soils with the same silty matrix differ instead, albeit in light form, from the clay in the 8 to 10 microns band, and this is represented in these figures. So you see, when we have different kind of emissivity, and you see here we have different characteristics of the same soils. For example, here you have different soils. Here you have different dimension of the molecules of this rocky medium. Here you have different, for example, characteristics of water content and so on. And you see that this is changing a lot if you are changing the parameters in which these spectral signatures are collected. Let's talk now about vegetation. Vegetation is a very singular spectral signature, and vegetation together with the water is a very important cover that we can find over the Earth's surface. So the spectral reflectance curve of vegetation is frequently indicated in remote sensing as the spectral signature par excellence. Its shape in the different wavelengths depend by the different factors analyzed below. So, what is important? Important is what is connected, as you can see here, with the leaf pigments. The portion of energy reflected in the visible, that is the acronym in English is VIS, field is related to the presence of leaf pigments such as chlorophyll, xanthophyll, and carotene. Chlorophyll, in particular, that represents more than 65% of the pigments of the leaves, is responsible for the two absorption bands. In blue, that is centered in 0.45 microns, and in red 0.66 microns, and the maximum relative reflectivity in green, that is around 0.5 microns, according to which the plant world. This effect is due in particular to chloroplasts, which contain granules where the different types of chlorophyll are located. Carotenes, on the other hand, impart those yellow-orange tones to poor or chlorophyll-free leaves. So that means that due to the leaf pigments, especially in the visible, the fraction especially of the red subband in the visible, this energy is almost completely absorbed. Why is completely absorbed? Because this energy is absorbed by the chlorophyll in order to run the photosynthesis. So that means that actually the vegetation, when want to start the photosynthesis, so when there's a phenological active state, so that means that the vegetation has leaves, and for example in spring they are of course putting the different leaves, and so the photosynthesis is active. This photosynthesis is based on the use of the red part of the visible spectrum, and so the chlorophyll is absorbing this kind of energy, while is not, the chlorophyll is not using the green part of the visible spectrum, and so if not, it's not absorbing this energy, being all the leaves of course opaque, and so without any transmission coefficient. That means if it's not using the green, it's going to reflect that part of energy, And that's why, I mean, when we are looking at some vegetation in general terms, of course, it's not always like that. But we are seeing the vegetation green because it's reflecting the green part of the visible spectrum, simply because it's not using this kind of energy that is ranging from 0.5 to 0.6 microns, that is the green band, for activating the photosynthesis mechanism by means of the chlorophyll. So this is the reason. So if you see in a positive phenological state, so when there's an improving of the vegetation, you don't have this kind of absorption in the red. So that means that the vegetation is not absorbing the red. And so the result is that, of course, being again the leaves opaque is reflecting the red, and so the leaves appears to be reddish. That means that, of course, the photosynthesis is not active. And that could be, for example, what is happening in autumn when the leaves are falling for most part of the vegetation, and before of falling they are becoming reddish because the chlorophyll is not absorbing anymore the red part of the spectrum. Or if we are in a period where the vegetation should improve, and I mean there's no more any absorption in the red, that means that we have some problems, some phytopathological problems, or for example problems related to the water content in the vegetation, or too much water, or not water enough in order to keep the vegetation in the same condition. The second characteristic that is very important for the spectral signature of the vegetation is the leaf structure. It is responsible for the spectral behavior in the near-infrared bands, that is called, the acronym is NIR, between 0.7 to 1.35 microns. By leaf structure, in this context, we mean the spatial organization of leaf cells, with reference to its morphological evidence, which varies from one species to another. Infrared radiation does not interact with chloroplasts, but is greatly influenced by the structure of the leaf, which causes a very high reflection, in order of 30–70% of the incident energy. So here you see, it's very clear, as when we composite a false color image, for example, for a thematic map sensor mounted on board of Landsat, the combination in RGB of 4, 3, 2, you see all the vegetation is red. Why is coming we are having this kind of representation? Because in the near infrared, the vegetation is reflecting a great part of the energy that is striking over it. So 30–70%. And as you can see on the images, this is the only surface on the Earth's surface that is reflecting so much in this part of the spectrum. And here, I'm sorry, what is important apart from that is also that the different species, being the leaf structure, they're responsible for this high reflectancy in the near infrared. This reflection you see here varies from one species to another. So that means that in the near infrared, taking into account how the vegetation is reflecting energy, there's a way to try to distinguish the different species of vegetation. Then the portion of residual energy is mainly transmitted, that is very little. In fact, on the same end, the foliar pigments and the cellulose that constitutes the cell walls are transparent, and on the other, the water contained in the leaf has weak absorption phenomena, less than 10%. At the beginning of the near-infrared interval, the reflectivity passes so abruptly from a few percentage points to values close to 50%, with a steep gradient around at 0.8 microns. the levels of the reflectivity plateau is higher, the more the tissue is made up of cells with irregular shapes and heterogeneous content. The reflectivity and then the transmissivity have similar values with a certain prevalence of the reflectivity, which can reach the limit value 80%, as in the case, for example, of olive tree. So I mean, for example, the olive tree are reflecting most part of the infrared. This phenomenon, in remote sensing, is of essential importance because it is the basis of the most significant analysis possibilities on the plant world. Whereas, you see here, the study of reflection in the near-infrared becomes a powerful investigation tool, both to discriminate different species, as I mentioned before, and to analyze the evolutionary stages and to determine possible pathologies within the same community. And so, this is why it's so important to check these characteristics of the leaf structure. Concerning the water content, that is the third very important characteristics, in the short wave infrared domain, the SWIR, between 1.35 and 2.7 microns, the spectral properties of vegetation strictly depend on the water content in the leaf, where, as we have seen, at 1.4, 1.9 and 2.6 microns, we have intense phenomena of absorption of radiation by water, while also the relative maximum of reflection at 1.65 microns and 2.2 microns are partially influenced by the water content of the leaves. In this way, the absorption wavelengths, as for soils, can become diagnostic with respect to the water stress of the plants. So I mean, as I mentioned during one labs, for example, if we are using ETM data, the sensor that is mounted on board of Landsat 7 or 8 platform, I mean, when we are using band 5, that is in the mid-infrared, band 5 is very sensitive to the water contact, not only for soils, but also for vegetation. So just taking into account this very narrow part of the electromagnetic spectra, we can in some way to have some diagnostic with respect to the water stress of the plants. So you see here we have a representation of the classical spectral signature of vegetation. You see we have here wavelengths on the x-axis ranging from 0.4 to 0.5 as before. This is here on the y we have the apparent reflectance that is of course here represented by the ranging, the variation of the rho coefficient, the reflectance coefficient ranging from 0 to 1. You see here we have the visible, the near infrared and then short wave infrared. And you see here we have how the vegetation here in the visible is reflecting from 0.4 to 0.7, and you see that having this reflectance relative maximum in the green, this kind of vegetation will appear green when observed by a human eye. Here we have the chlorophyll absorption in the blue and in the red band, you see here. Here we have in the cell, the near infrared, due to the cell structure, high reflectance of vegetation in this part of the band. Here is the red edge. You see that's a very rapid change of reflectivity passing through 0.7 to 0.8, while in the short wave infrared that is related to water content, leaf biochemicals, protein, lignin, cellulose, etc. We have here, you see, in these 3 points, the atmospheric water absorption bands. So it's not really due to the vegetation, but is due mainly, as we mentioned when we faced the topics related to the interaction between the electromagnetic energy and the atmosphere, is of course due to the lack of atmospheric windows in this part of the electromagnetic spectra. All right. you see here, this is in these figures we can represent again from 0.4 to 2.5, so starting from the blue to the mid-infrared, and we have here the rho coefficient on the y. We are representing a different kind of vegetation. So you see that while, for example, these purple, green, and maroon spectral signature that are representing conifer, deciduous, and green grass, you see they are very similar, especially here in the visible. You see here they are very similar. When we are ranging in the when we are going to the near infrared, you see that there are some differences, especially for this yellow grass, and of course these are the part of the especially the near infrared. This is the part of the spectrum in which you can distinguish, as we mentioned before, different kind of vegetation. Okay, from the emissive point of view, the vegetation behaves very differently depending on the water content, as demonstrated in the examples. So you see here that when we are taking into consideration, you see in the x-axis we have wavelengths that are ranging from around 8 to 12 microns. So I mean these are not really spectral signature, because the spectral signature are related to the reflectance phenomena. Here we are talking about emission, and you see here we have on the y the emission coefficient, that is the epsilon, that is ranging from 0 to 1. You see that, I mean, if we are taking into consideration green grass, dry grass of this particular soil, you see that the emission curves that are not spectral signature, of course, they are very dissimilar. And so from this diagram, the emissivity trend of a grass lawn in vegetative condition could be assimilated to a black body with values close to the unity over the entire spectral range of the medium and thermal infrared from 3 to 14 microns. You see here the green grass. The green grass, from the emission point of view, has values that are very similar to 1. So, as is stated here, it's a behavior that is very similar to a black body. Instead, clearly differentiated behaviors occurs in two medium wave and thermal infrared windows. Why, for example, you see here, if we have dry grass, so with a very small percentage of water content, I mean especially in the thermal infrared here from 10 to 12 microns, the emissivity is lower than of, for example, green grass with a larger amount of water. So, I mean, we can distinguish in some way also different kind of species if using thermal infrared acquired images. But you will see that due for, especially to the geometric resolution of these images, this kind of distinction between different kind of vegetation is not so simple. Okay, with that I think that we can close what we introduced today, that is the interaction between the electromagnetic energy and the surfaces. In the second part, we analyze what is the topics related to the spectral characteristics. So how the different surfaces the reflection is different in these, is changing the different wavelengths. And so with this part we are considering finished the lecture number 5, that is related to the interaction between the electromagnetic energy and the surface. So after around 1 hour we can close this second part of the lecture. Take care, and as usual we are at home, and we are staying at home, just attending these very nice lectures. Bye.